Now we are focusing on another type of hybridization, that is sp2 hybridization. Now this is time to get answers of certain questions we discussed in earlier way. Say for example, when we were discussing certain limitations of VBT, that is valence bond theory, we discussed about BF3 molecule, that is boron trifluoride molecule. Now we are here to discuss structure of boron trifluoride molecule or BF3 molecule. Let us check out. I am writing name BF3. You are aware that we discussed it earlier that BF3 molecule should be not form, actually it should be BF and not BF3, but now we have to discuss how it is forming a stable molecule. Now you are aware the central atom, that is boron, atomic number 5. So electronic configuration 1s2, then 2s2, after 2s2 it is 2p, so it is 2p1. But you are aware that now we have to show box diagram for last shell. So it is 2s, then 3 degenerated orbital, that is 2px, 2py, 2pz. Try to recollect px, py, pz we are calling as magnetic quantum number, whereas 2, that is principal quantum number, p, that is azimuthal quantum number. So like that we discussed. So here it is 2s and 2px, 2py, 2pz. Now these 3 orbitals we are calling as degenerated orbitals. What is the meaning of degenerated orbital? Energy level of these 3 orbitals, that is same, whereas here 2s is having different energy. Now in 2s there are 2 electrons. So according to spin quantum number, one must be clockwise, then another must be anti-clockwise. So here we are getting clockwise and anti-clockwise 2 electrons. Now here alphabetically I am placing this electron over here. It can be anywhere because all 3 orbitals possess same energy, and that's why we are calling these 3 orbitals as degenerated orbitals. Now this electron is there alphabetically I have placed in 2px. So there are 3 electrons. 3 bonds formation should be there with fluorine, because you are aware electronic configuration of fluorine. Here only I am writing it is 1s2, 2s2, 2px2, 2py2 and 2pz1. So try to recollect this electronic configuration we have discussed. There is only one unpaired electron in 2pz. So that one electron can form bond with this. So only one bond formation is there. What about rest 2 fluorine? So here we are going to get hybridization. This we are calling as ground state. In this ground state we have 2s and 2p as separated, but now we are giving energy. Now this energy is called as energy of activation, where with supply of energy electron get excited. So this is excited state. In excited state the electron from 2s get excited to higher level. So one electron is here, one electron is here, and one electron from this get excited to higher level. Alphabetically I am placing it into 2py. Not necessary, but here I am going by alphabetical order in order to get clear concepts. So this state is called as excited state, but on excited state formation there is hybrid state. Now in this case electron from 2s is entering in 2py, but there is no question of 2pz. So 2 orbitals of p and 1 orbital of s only undergoing hybridization, whereas this orbital will remain unhybridized. So in case of hybrid state we are getting this type of structure. So here I have to say this is sp2 hybridized orbitals, Why sp2? Because one of s and two of p, they are combining together. So they are called as sp2 hybridized orbital, whereas this is unhybridized orbital. So this unhybridized is 2pz. So this is, I am keeping separate than hybridized. So we are calling this as unhybridized orbital. Whereas these orbitals are sp3 hybridized orbital. Each orbital is now possessing out one electron, that is unpaired electron. Whereas 3 fluorine, they are having pz orbital vacant. Only one electron in pz orbital. So single electron or unpaired electron of pz orbital is overlapping with these 3 orbitals and bond formation is there. So this is hybrid structure. Please take it down. Why take it down? Because I had to make here structural diagram now. So please take this down and we are going to make structural diagram over here. Now we have to place these orbitals. Now you are aware that pz orbital, okay, here I want to take you to some different topic. Say when this way orbital is there, you are aware this is, I can name px, py or pz. So this is first orbital. Now this is going to overlap with another orbital. Say this orbital is another p orbital. We are calling this as pp overlap. When there is overlap, here the overlapping orbitals are in this way that there should be maximum electron density between two nuclei, and for that purpose the shape of orbitals, that is going to change. So in case of bonding, this orbital, as I am showing here, symmetrical, this become unsymmetrical. As we have discussed in earlier part of hybrid orbital, we discussed that major lobe and minor lobe. Same way here, this orbital will change out its nature and this way it will form minor lobe and major lobe, and then there is practically overlap. So this is the overlap. So this is situation at bonding. Now here one orbital is s and two orbitals are p. As two orbitals are p, they are at 90 degree to each other, because you are aware px, py, pz, x axis, y axis and z axis, they are having 90 degree to each other, perpendicular to each other, whereas s orbital is spherical in shape. So by combining this, 3 orbitals will get formed. So these 3 orbitals should be placed in space in such a way that there should be maximum distance between them and minimum repulsion between them. I am using word again, there must be maximum distance between them and minimum repulsion between them. So this situation, we are having structure like, I should not draw actually axis over here. So instead of that, I am drawing this way. One orbital, major lobe here and minor lobe here. Say, try to locate somewhat spherical part. It is not exact spherical, but not as dumbbell shape also. Somewhat bulging out. Why? Because S character is more in sp2 hybridization. Earlier hybridization we discussed, that was sp3. In that one orbital was s and 3 orbitals were p. So out of 4 orbital, one was s. That means 25% orbital was s. That is 1/4. That means 25% s character was there. And that's why in that case orbitals were not so bulgy. But in this case, out of 3 orbital, one is s. This is called as S character. So S character is now 33.33%. Check out 1/3 into 100. So 100 by 3. So answer is 33.33. You can calculate and check out. So here this lobe is having somewhat more bulging out, whereas another orbital I have to place as much as away from that. You may ask question, why not this way? Okay, let us check out another way. Say this is some forest, very very dense forest, circular in shape. Suppose this is the diameter of that forest. This is diameter as 10 kilometer. You are alone and you are asked to enter in this forest. Let us check out from this side. You are entering in the forest. Just try to guess answer. What is the distance that you can go inside the forest? 1 kilometer, 2 kilometer. What is the distance that you can travel inside the forest? Check out your own capacity. Somebody say, I will not enter at all. No, you have courage now. Try to enter. And how much you can enter inside the forest? Listen the question carefully. How much you can enter inside the forest? Okay. My answer is that with all my courage, I can maximum go 5 kilometers inside the forest. Not more than that. Why? The moment I am coming here at 5 kilometer distance, this is the center of forest, and from that if I traveled, I can travel, but while I am traveling this distance, I am not going inside the forest, I am coming outside the forest. So apply this concept over here. I am placing this orbital away. So suppose I am placing it exactly diagonally opposite direction, then where is to place third orbital? That is the question. And for that purpose, we have to arrange them in this way, that third orbital in this direction, this is minor lobe. What should be the angle? Because this is planar structure. The earlier structure was not planar structure. Earlier structure was three-dimensional. Earlier means sp3 hybridization structure. So that was three-dimensional structure. Whereas bond angle was 109.28 or 109 degree and 28 minutes. Here the structure is planar. So only x-axis and y-axis are there. There is no question of z-axis applicable for this structure. So where I have to place this in the circle? What is the degrees of circle? That is 360 degree. Divide it into 3 lobes. So 360 divided by 3, we will get answer as 120 degree. So maximum distance should be here. That should be 120 degrees. Same way here. Answer is 120 degree. And remaining, that answer is also 120 degree. So this way we have a structure that is planar structure with bond angle 120 degree. Like that 3 possible lobes are there. These 3 possible lobes are there because of boron. So this is central atom. Now fluorine, that 2pz electron, that electron is overlapping with this. Now try to recollect. It is p orbital. But fluorine is not undergoing hybridization. And for that purpose, its orbital is pure. Say, when I am saying unhybridized, it is indicated. We are many times calling this as pure orbital. So here we have to say either pure or unhybridized orbital. Now here I am showing in different color the fluorine orbital. Now you are aware p orbital. So p orbital is having dumbbell shape. But when bonding condition is there, the dumbbell shape is changed out into lobe structure, and the one become major lobe and another become minor lobe. So this is what pz or 2pz orbital of fluorine. Same way here and same way here. So all these orbitals, they are of fluorine. So this is the structure of boron trifluoride. Now in this diagram I can show this way, but otherwise this structure I can show this way. The boron is at center with 3 bonds of fluorine with bond angle 120 degree. So this is the structure of boron trifluoride or BF3. So try to take it down, and I am sure you are not able to follow these concepts immediately. For that purpose you have to revise these videos twice, thrice you have to observe these videos, then you will get clear-cut ideas. And one book I must recommend over here, that is 11th standard or 12th standard chemistry textbooks, NCRT or any other book you can refer in order to get more knowledge about this hybridization concept. Apart from that, O.P. Agarwal's books, they are also very good for understanding these concepts. So in various ways you will get these concepts, so try to read from these books also. Only our lectures are not sufficient. Your external reading is really helpful to get more and more knowledge in this concept. So this is the structure of BF3. I am summarizing this structure. In this case, the boron is having electronic configuration as 1s2, 2s2, 2p1. So ground state configuration I have to show 2s2, and 2p I have to split out as 2px1. In excited state, one electron get excited from 2s to 2p. So as these 3 orbitals are undergoing hybridization, we are calling this hybridization as sp2 hybridization, whereas this orbital is called as pure orbital or unhybridized orbital. 2pz will not participate. This orbital is there, but it is vacant orbital. It will not participate. So these 3 orbitals must be placed at equidistance, but as long as possible. And so we are getting their bond angle as 120 degree. The structure is planar. So this way we are getting boron trifluoride. Here orbitals of fluorine, that is 2pz orbitals of fluorine, they are overlapping with each other. And here I am getting you dash structure. What is exactly dash structure of BF3? That is shown over here. So this is the first example of sp2 hybridization, and we are moving not simpler one but more complicated structure right now, that is C2H4 molecule. We are now switching to the structure that is C2H4 structure. So first thing I am writing about molecule name, that is C2H4. This is ethene in UPSC, but we have not discussed this topic yet. So right now just keep in mind the molecule. This molecule is called as ethene in IUPSC nomenclature. So we have to discuss this structure. Technically speaking, you are aware carbon is tetravalent. Tetra means 4. So carbon is having 4 valencies. Hydrogen is monovalent. So this is one hydrogen, this is one hydrogen, this is one hydrogen, this is another hydrogen. So net 2 bonds of carbon, they are satisfied. What about rest of 2 bonds? Because each carbon should have 4 bonds and each hydrogen should have 1 bond. So hydrogen is satisfied. Now no more bonds are formed between hydrogen. So only formation of bond is there between carbon and carbon. And so the 2 bonds are formed in case of carbon. Now when there is this type of bond formation, this is called as double bond. When this type of double bonds are formed, one bond is strong bond. It is denoted by letter, don't read as 6. This is called as sigma. And so this is sigma bond between one carbon and one carbon. This is stronger bond. Whereas another bond is weak bond. It is again denoted by letter pi. So when this type of bonds are there, there are 2. That is sigma bond and pi bond. So in this double bond, first is strong and second is weak. So this is the structure of ethene. Now this is what structure we are discussing out here, that is only on basis of this bonding nature. But now we have to discuss this structure with VBT and application of hybridization concepts. For that purpose, I have to account that there must be double bond between carbon and carbon. Out of that, one bond is strong and one bond is weak. Whereas there are single bonds between carbon and hydrogen. If single bond is there, then there is no question. They are all single bonds. So they are not, we are saying distinguishing as sigma and pi. But when double bonds are there, we have to distinguish between sigma and pi. In order to explain this ethene, I have to write down again same thing. First, hydrogen. Electronic configuration, now you are aware 1s1. Carbon, you are aware atomic number is 6. So electronic configuration 1s2, 2s2 and 2p2. Then I have to show ground state configuration. So ground state configuration 2s, then 2px, 2py, 2pz. Okay, one more suggestion is there. Now from previous lectures, we are drawing out these diagrams again and again. So we discuss about methane, we discuss about ammonia, we discuss about water molecule. Now we discuss about BF3. So you are also familiar with this type of activity. So try to draw with me. So this is just copy paste, like I am explaining that structure again and again. So we discuss in carbon the same here. So here there are 2 electrons, 2s2. Then these orbitals are degenerated orbital, magnetic quantum number px, py, pz. I have to fill out electron by using Hund's rule of maximum multiplicity. So if one electron is here, second electron will not go here. It will remain unpaired. So either here or here. But alphabetically we are placing in px and py. Whereas here there's energy gap and therefore this electron will not move here. This electron will remain here. So this is ground state configuration. Now excited state. Just now I said this electron will not move here. Why? Because there is energy gap. But suppose energy is supplied, then this electron can move at higher level. So that is we are calling as excited state. We are supplying that energy and then that electron can be transferred to higher level. So on supply of energy, this electron will move over here. So I am having now one unpaired electron, 2, 3 and 4. Till here everything is there with similar to methane. In that methane molecule also we discuss all these facts. I have just revised that facts. But in case of hybrid state, we have different structure. What is that different structure? That here first, second and third, they are going to hybridize. Whereas this electron will remain unhybridized. No doubt that all are having initially equal energy, but now this is not hybridizing. Try to recollect First World War. There was groupism. In that Germany, then Austria, Italy and Turkey or Turkestan, they were formed a group. Whereas opposition group was England, France, then Russia and USA, that is America. But practically when war was there, at that time Germany was there in war, Austria was there in war and Turkey was there in war. But Italy was not declared out war. And in latter phase, Italy declared war, but that is against Germany, not with the side of Germany. So this way, something is happened. The same thing is here, that till here these orbitals are participating. But to the surprise, suddenly this orbital is not participating out. Why this orbital will not participating out? Because we have to account for second bond. we'll get idea afterward. First try to understand the concept as it is. Assume, rather understand, please try to assume. Now this electron is here, this is here, this is here. So as all these three electrons are undergoing hybridization, we are giving this name as sp2 hybridization structure. Whereas this electron will remain here. I may mark it as 2pz, or I should say any orbital. 2p orbital is there. This is unhybridized orbital, or rather I should use word here pure orbital. So this is unhybridized or pure orbital. So this way sp2 hybridization and one orbital remain unhybridized. Try to recollect, in case of BF3, this orbital was there, unhybridized, but at that time electron was not there, and now there is electron that is there in 2pz orbital, or 2p orbital we should say right now. Now try to get this concept. Why we'll discuss afterwards, but right now try to get the situation. So this is somewhat similar situation to BF3. Why somewhat? Because in case of BF3 this orbital was empty or vacant, whereas here this orbital is possessing out electron, that is unpaired electron. Now we are going to structure. So as sp3 hybridization is there, first carbon will be like this. We are aware now, when bonding condition is there, there is major lobe and minor lobe. The second orbital will be like that, and the third orbital every time will get bond angle 120 degree. Here also 120, here also 120 degree. The second carbon, say as I have written here configuration of carbon. So first carbon is having same, second is also having same. So second carbon is also undergoing same situation, and then second carbon will form this type of overlap here. First bond, second and third. Here also I should say everywhere bond angle is 120 degree. This is practical overlap between hybridized sp orbital, hybridized sp2 orbital. They are overlapping with each other. Now hydrogen, you are aware hydrogen is having 1s1. In case of BF3 we discuss about fluorine, and at that time shape of orbital was dumbbell, but here the shape of orbital is spherical in shape. So I have to show these orbitals are overlapping. These orbitals are s orbital of hydrogen. This is carbon and this is also carbon. So this way there is overlap. So this is overlap, this is and this is. So all four hydrogen we satisfactorily shown. The axial overlap, what is axial? Along axis these two overlaps, they are also there. So all bonds are shown, but only one bond is not shown, that carbon-carbon should have double bond. But here we have carbon-carbon single bond. So for that purpose this orbital is there. This is unhybridized p orbital. Now this unhybridized p orbital is perpendicular to hybridized orbital. So perpendicular means I have to show one orbital over here and another orbital over here. Try to see the situation. These orbitals are facing towards you, but I can't draw it over here, and so I have to show in somewhat complicated manner, like, but you have to imagine these orbitals are perpendicular to each other, and now there is overlap between these orbitals. Now this overlap practically I can't show here, but somewhat weaker overlap is there. So these orbitals try to fuse here. Don't say two bonds are formed. When one orbital and one orbital combine, only one bond formation is there. This is called as lateral overlap. The lateral overlap is very, very weak. This is forming pi bond. So try to guess the concept. The first bond formed between carbon and carbon, this overlap is along the axis, and therefore this is called as axial overlap, whereas the extent of overlap is very, very high. So this bond is called as sigma bond, which is very, very strong bond. But This overlap, practically I am not able to show also. So they are showing like this, that these orbitals are forming cloud over here and these clouds are mixed out. But this overlap is very, very weak overlap, and that's why the bond is not strong bond. So second bond is formed, but that is not that strong. But bond is there. We are calling that bond as pi bond. So this way we have 4 bond formation, first, second and third. The 3 bonds, they are strong bond, but fourth bond is very, very weak. And that's why when we are calling the reaction, so what is the, let us, before reaction we are going to discuss this structure. So what is the expected structure over here? That this is the structure. So initially I have drawn there, I was showing hydrogen here and here. That is not schema, that is just schematic, not real one. Whereas now it is very clear for you that what is the angle here, that is 120 degree. What is angle over here? 120 degree. Angle over here 120 degree. So check out any angle. In this case we are getting angle as 120 degree only. So this way we are getting lateral overlap between carbon and carbon, that is giving us pi bond. Whereas axial overlap between carbon and carbon, that is giving me sigma bond. So both bond I must show here. So sigma and pi. So in this structure we discuss about sigma bonding and pi bonding. So first we discuss about BF3 and then we discuss about C2H4, that is structure of ethene. Now this portion is theoretical one. This is very, very helpful for you when we are discussing about organic chemistry particularly, because in case of organic chemistry, or rather I should say chemistry of carbon compounds. So when we are studying out chemistry of carbon compounds, these type of concepts are helpful. Now I am focusing over the concept, the bond energy. What is bond energy? The energy required to break a bond. Okay, forget. Again keep in mind, basic principle. When bond is formed, energy is evolved. Try to recollect postulates of valence bond theory. Bond formation is pairing up of electron, and when this type of pairing up of electrons are there, then at that time the attractive forces increases. As a result, energy lower down. So that energy of system lower down, that is, it is throwing out energy, and that's why try to recollect potential energy curve diagram we have discussed. In case of bonding situation, potential energy of system decreases. So here also keep in mind, when bond formation is there, energy is evolved. In order to break the bond, we have to supply that much amount of energy. Then only one can rupture the bond. So keep in mind 2 laws. Actually it is reciprocal of law. Say, in order the bond formation is there, energy is evolved. I am revising. Bond formation is there, energy is evolved. In order to rupture the bond, we have to supply energy. Alright. So bond making, energy evolved. Bond breaking, energy required. Bond making, energy evolved. Bond breaking, energy required. Clear? So what is the amount of energy required to rupture or required to break a bond? That is called as bond energy. In other words, it is called as bond dissociation energy, but right now we can say only bond energy. So bond energy for pi bond is very, very less, and for sigma bond it is high. So what is the bond that is undergoing breakdown first, having low energy? Say I am giving you example. Suppose you have only 2000 rupees in your pocket. You don't have credit card also, and the shopkeeper is not ready to give you any credit. You want to purchase out mobile phone. Some pieces of mobile phone, they are very, very excellent, costing you some 40,000 rupees. Some mobile may have 60,000 rupees. Some may have 15,000 rupees. and some may cost just 1000 rupees. What will you do in this situation? Because you want a mobile phone for communication purpose basically, and for that purpose 1000 rupees are also we are getting some phone, and 60,000 rupees also you are getting some phone, but you have only 2000, so you can purchase out only 1000 rupees phone. Get concept? The cost is also playing important role. A person like me, I will always prefer that lower cost and not higher. What is the basic purpose of mobile phone? Communication. So phone, that communication should be there. For that purpose phone is required, and not for playing games. Camera, additional ability required. But I will not purchase out phone that will cost me 40,000 or 60,000 rupees. But here there are people who are purchasing only upper limits also. But for that purpose they must have money. Then only they can purchase out, or credit card. Rather you have to pay later on. The same consideration was here, that we have to break two bonds. This will cost some 100 kilojoule per mole energy, and this will cost 500 kilojoule per mole energy. So if bond we are supplying energy, the first energy is absorbed by this case only. This will not go to higher level, and first reaction or bond breaking is carried out over here. So for example, if this compound is allowed to react with hydrogen chloride, HCl gas, what will the situation? The pi bond is weaker, so carbon-carbon will they are not that strong, they will open out, and we are getting two sites more for bonding, and then one will occupy hydrogen and one will occupy chlorine. So this bond will not break out, only pi bond will break out, and that's why the compound that is having, this is ethene, this is ethyl chloride. So this bond will not break out and carbon-carbon will not separate out, because this bond is stronger, whereas the pi bond is weaker, and therefore many times in this case we are getting that reactions occur along with double bond, because pi bonds simply that is breaking down the price. So same way, having very low energy, so it can rupture very easily. So first all pi bond will consume that energy to break down that bond, and not sigma bond. So this way we are getting the reactivity at pi bond is very, very high. And so if compound is possessing out pi bond, then it is having more chance to get reaction. Usually this type of reactions we are calling as addition type reaction, because nobody is move away. HCl is reacted, so hydrogen is attached over here and chlorine is attached over here. So nothing is coming out, only addition is there. So this type of reactions we are calling addition reaction. So when there is presence of pi bond, usually addition reactions are there. Usually reaction takes place along pi bond only. Why again and again I am using word usually? Because there are certain examples like benzene where pi bond is not ruptured out, but reasons are different, we will discuss later on. Now we are switching over to hybridization concept, that is SP hybridization. Now in this SP hybridization we have to discuss about BCl2. So as previous structure we are writing out here, first one, that is formula BeCl2. Now you are aware, first peripheral, this is peripheral atom, so I am writing out chlorine, atomic number 17, you are aware, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. Whereas P shell is last shell, I can write down this way also, 3px2, 3py2 and 3pz2. Sorry, 3pz1. So we are now clear that in last orbital there is only one electron, that is 3pz1. Now second, this is central atom, B here, atomic number 4. Beryllium is central atom, atomic number 4. So electronic configuration 1s2 and 2s2, whereas 2p 0. I should not write actually 2p 0, but in order to further discussion we require this, therefore I am writing. So what is ground state configuration? So ground state configuration is 2s and 2p. So here 2px, 2py and 2pz. In 2s there are 2 electrons, but 2p there are 0 electrons. Now here these orbitals are there, but they are vacant. Degenerated orbitals are there, but they are vacant, whereas here 2 electrons are there. Now we discussed that B is divalent, but according to VBT, as no unpaired electrons are here, it should not form any bond. But in an excited state, one electron from 2s get excited to higher level. As a result, we are getting a hybrid state, that is consisting of 2 electrons here. So one here and one here. They are mixing out and recasting their orbital. Recasting means rebuilding. So here recasting their orbital. So one of S and one of P. So we are getting name as sp1, I should say, or s1p1, but we are saying sp. So this is sp hybridized orbitals. Whereas these two orbitals, say electrons are not there, but orbitals are there. So these two orbitals are remaining unhybridized. So I should say these orbitals are unhybridized orbital, or rather I should say these orbitals are pure orbitals. So this way we are getting hybridized orbitals as sp, whereas this is unhybridized orbital. Now here, in order to get structure, I must consider beryllium as central atom. Now we are making drawing of this. So first orbital, should I show this way or still more? That is, try to guess why. Say here S character is more. Now out of 2 orbitals, one is S and one is P. S orbital is spherical in shape, P orbital is dumbbell in shape, and therefore S character is 50%. Out of 2, one orbital is S. So try to recollect, in sp3 hybridization, S character was just 25%. Out of 4 orbitals, one was S. In sp3 hybridization, out of 3 orbitals, one was S. And now in sp hybridization, out of 2 orbitals, one is S. And therefore this is bulging out. So this is according to axis. So this is first lobe, where I should place second lobe. The second lobe is diagonally opposite, because there must be maximum displacement, maximum distance and minimum repulsion. So in order to get that, I should show second lobe over here, a minor or smaller lobe over here. Now there is chlorine pz orbital, that is overlapping anyway, but here important thing is that these 2 lobes are kept as much as away from each other. In previous example there were 3 lobes, so bond angle was 120, but structure was planar. Now here the bond angle is 180 and structure is planar, yes, in plane, but it is called as linear structure. Moreover, I should say it is along with one line, and so this structure is linear. So again revising, when there is question of sp2 hybridization, the structure was planar. Then there was structure sp3, it was 3-dimensional. Get this way, the first orbital like this, whereas 3 orbitals, they are like this, they are at bottom. So 3-dimensional structure was there, this was called as tetrahedral structure. Whereas in case of sp2, it was planar structure. And now in this case of sp, it is linear structure. Now I have to show chlorine. So chlorine is 3pz. As it is pz, overlapping orbital. So this way I can show it is dumbbell shape. One major lobe, one minor lobe. So this is Cl, this is 3pz orbital. Same way here. So this is also Cl, 3pz orbital, overlapping like this, whereas this is central atom. No doubt diagram is not proportional one, but in order to explain how overlap this is there, the bond angle here, this is 180 degree. So structure is linear, and this way boron dichloride or BeCl2 is existing out here. This is the answer why beryllium is undergoing reaction, and it should be inert, but practically it is giving me structure that is divalent structure. So this is the structure, this is more stable structure because S character is more. So this is the structure of BeCl2. In other words, I should write this way: B, this is one Cl and this is another Cl with bond angle 180 degree. So this is the structure of BeCl2. Other structures similar to that you have to search from periodic table. In next chapter we are going to discuss periodic table, and so try to write down your own structure. Try to make out this type of structures. Only these hybridizations are not there. Apart from that, various hybridizations are there. I am giving you very basic level of hybridization. So we discuss here only 3, that is sp3, sp2 and sp. Now we have to discuss about next structure, that is structure of C2H2, the complicated one. This is simple example of this hybridization. Now we are discussing complicated example of this hybridization. So be present mentally also. There must be notebook in your hand and you should also write down along with me. We are now discussing about C2H2 structure. I am writing out, it is C2H2. This is called as, in IUPSC, we are calling this as ethyne. So end suffix is what the word we are attaching at end of this. So here suffix is attached, that is ethyne. YNE is suffix that is attached to it. So this indicate C2H2. Now I have to assign structure manually here first, that is carbon is tetravalent and hydrogen is divalent. Tetra means you are aware now 4. So there are 2 carbon atoms, 2 hydrogen atoms. So I am assigning 1 hydrogen over here, 1 hydrogen over here. So valency of hydrogen is satisfied. Carbon is tetravalent, so there are 4 bonds, but here there is only 1 bond between carbon and hydrogen. I can assign another bond between carbon and hydrogen. This way carbon is divalent and hydrogen is monovalent, satisfied, but carbon is tetravalent in this structure. How to give us the structure tetravalent? And for that purpose we are assuming there is formation of double bond twice. So twice double bond means total net number of bonds are there 3. So this type of arrangement is practically possible for carbon only in the group. In next lecture periodic table we are discussing, but next element of carbon in the group is silicon. Silicon is not undergoing this type of arrangement, but in the group carbon is undergoing this type of arrangement. Nitrogen, that is not in the group of carbon, but nitrogen can also form triple bond between them. Now here I am talking of carbon. So first bond you are aware of, obviously that first bond we are saying axial overlap, that is sigma bond, whereas 2 bonds they are now, we are aware that is because of lateral overlap, they are called as pi bonds. So pi bonds are much more weaker than sigma bond, and now presence of 2 pi bond, that means you can easily guess the molecule is highly unstable. What is unstable? It is tend for reaction. So by supply of little amount of energy, pi bond will rupture out and molecule will undergo fast reaction. So that's why this ethine molecule is very, very highly reactive. The reason is that it is consisting of 2 pi bonds. Anyway, so this is about the structure. Now we have to explain exactly what is the structure of this molecule with our valence bond theory introduced in concept of hybridization. So let us check out. You are aware now, first atom, that is peripheral, I am writing here atomic number 1, hydrogen, electronic configuration is 1s1, whereas second atom, this is carbon, you are aware atomic number is 6, electronic configuration, try to write along with me, that is 1s2, 2s2, 2p2, but you are aware p shell is last, so we have to split out, and I am giving you ground state configuration 2s, 2px, 2py, 2pz. So 2s, these 3 orbitals are degenerated, so 1 electron each over here. Alphabetically I am placing in px and py. Now this is ground state. Now we have to go for excited state. In this excited state, it is very clear that this electron is moving to a higher orbital, so we are getting excited structure, and now hybrid structure, because there is mixing and recasting of orbitals. So as there is concept of mixing and recasting of orbital, now in this mixing only 1 and 1 is coming for mixing, so we are getting here sp hybrid structure, whereas these 2 orbitals are unhybridized, or we are calling this as pure orbital. So they are not taking part in the reaction, but as it is either py and pz, they are having perpendicular to each other, whereas this is in one plane. Now we are assigning a structure. So as carbon is there, which is undergoing sp hybridization, so first carbon and second carbon, so I am assigning molecular structure of first carbon. You are aware now this is major lobe, this is minor lobe. Along with this carbon, major lobe and minor lobe. Now this is another orbital having angle as 180 degrees. So one is facing this side, one is facing this side. So major lobe, minor lobe. So this is carbon atom. This is another carbon atom. Here we are getting major lobe and minor lobe. Now it is overlapping with electron of hydrogen. So this way I should show electron of hydrogen over here. So hydrogen is having s orbital. So this is overlap of hydrogen, hydrogen. Now one orbital of this py, let us take, which is coming out perpendicular to this board, whereas another orbital is in this direction. So we are getting totally like this system, coordinate system, x, y and z. So these 2 orbital I am not able to show over here, so I am showing in different colors. So in blue color I am showing one orbital. Now you have to imagine there is overlap between these 2 getting one bond. whereas another orbital that I am showing in red color, that is coming outside. So this way I am showing, and there is overlap between these two orbital. So this way these overlaps are lateral, whereas in black color shown overlap, they are axial. So this is giving me sigma bond, whereas these two, this will give me one pi bond, whereas this will give me another pi bond. So pi 1 and pi 2, third bond is sigma. So this is the structure of ethyne molecule, that is C2H2. Practically I can show this molecule like this way, triple bond, this is one hydrogen, so molecule structure is linear, geometry of molecule is linear. This is sigma bond and these two bonds are pi bonds. So this way we are getting structure of ethene molecule. So this way we discuss about chemical bonding. In this chemical bonding part, we discuss about first type of bond, that is ionic bond, then covalent bond, and then third bond we have not discussed, that is coordinate bond. We have to discuss it, but in later phase. Now in case of bond formation, we discuss electronic theory of valency, then we discuss valence bond theory, and then we discuss the third concept, that is hybridization concept, that is introduced in valence bond theory. In valence bond theory, we discuss how hydrogen molecule is formed, then we discuss why not He2 molecule is formed, then we discuss need of concept of hybridization, then we discuss hybridization, steps involved in hybridization, and then we discuss various types of hybridization. Out of that, sp3, sp2 and sp. These three hybridizations we discuss at depth. And now we are switching over to another topic in chemical bonding, that is molecular orbital theory.